that have been described and implemented in the industry: deterministic and probabilistic. Now, in deterministic analysis, all data used for the analysis is actually known beforehand. And the other one, probabilistic, this is actually done assuming the likelihood that something will or has happened, but you actually don't know exactly when or how it actually happened. Now, probabilistic methods institute powerful tools for use in many kinds, of decision-making problems, and in this case, of course, cybersecurity analysis, right? In this type of analysis, the probability, of something that actually will happen is what, is the core of that analysis, right? Now, in the deterministic analysis, you know and obtain facts about the incident or the breach, and also the affected applications and potentially even the threat actor, of that incident, right? Now, for example, by analyzing applications based on port-based analysis and similar methods, you can assume that the process is actually deterministic, especially when applications conform to the specifications and to what is actually expected. Now, unfortunately, some of these applications do not follow these rules, and a good example of this is actually peer-to-peer applications, which actually try to evade firewalls using ephemeral ports or negotiated ports. And this is why, in many cases, probabilistic analysis is actually done versus deterministic analysis.
Now, the miscreants or the bad guys, they actually have to be right only once to do harm. In order to protect your network, you must have a balance between visibility and between control. You must combine tools like network metadata extraction, NetFlow, malware detection, IPS, threat intelligence, full packet capture, server and endpoint logs, and much more, right? This is actually easier said than done, right? Complexity is actually the enemy of security, right? The more complex your environment, the harder it is to monitor and protect it. Now, you want to reach a good point where the capability of the security monitoring tool you actually have deployed is greater than the complexity involved managing such tools or such products, right? You can never get a 100% secure network. No product of any size, any type of vendors, or any type of security products can actually provide you 100% security at a given time. So, antivirus and firewalls are not just enough to stop advanced targeted attacks. You actually must have a balance between products, people, and processes in order to successfully monitor and protect your network. You should always assume that your network is actually compromised and think like an attacker. Now, in previous lessons, you learned what is defense in depth. You must apply these concepts to successfully monitor your network. Use a layered onion diagram to understand how to protect your critical assets and how to place visibility and control tools within your network. These layer diagrams actually will help you understand the traffic flows and where you actually have security gaps and how to deploy technologies, security technologies and visibility technologies to close those gaps. You must also understand what you're looking for, right? Things like connections to command and control servers, indicators of compromise, internal botnet traffic, DNS resolvers, and much more. So again, always assume that your network has been compromised and think like an attacker. You need security monitoring tools, right? So this includes a traditional and next generation intrusion detection and prevention systems, anomaly detection to look for frequent, large or lengthy network sessions, and many more, right? In the Security Operations Center, you actually have to combine, this type of tools and also use threat intelligence. So combine the telemetry information, gathered from, IPS, firewall, server logs, and everything, but correlate them with threat intelligence, right? And threat intelligence are used for event research and analysis, right? So this threat intelligence can be imported into alerting tools to add detection and fidelity, right? Also deploy malware analysis tools to detect and block malware and zero-day exploits, right? As you learn in Lesson 10, you can deploy full packet capture to see everything that is happening in your network. However, this requires large amounts of storage space, but can be very useful for forensics, right? You can deploy things like NetFlow, Bro, T-Shark, and other tools to actually obtain packet metadata instead of full packet capture. And this actually is done since it doesn't require as much storage space as full packet captures, of course. Cisco offers a managed security service where customers outsource their security operations center activities to Cisco. The service is actually called the Active Threat Analytics, or ATA. I'm including the high-level review of the architecture of that service so you can actually get an idea of the tools involved in the security operations center, right? And what are the tools that actually, at least some of the tools that Cisco uses for that service and in the security operations centers that they have around the world, right? Cisco created an open source big data security analytics framework called OpenSOC, or the Open Security Operations Center. It was actually designed to consume and monitor network traffic from their customers, right? And specifically in large environments, right? Because it's very scalable. Now, OpenSOC was then evolved into Apache Metron. And Apache Metron is a framework that allows you to consume, process, and analyze telemetry for many, many different vendors and different products, right? I'm including a link to Metron's website and their GitHub repository here for your reference. Benefits for security and privacy, but in the world of incident response and forensics, encryption introduces several challenges. Even law enforcement agencies actually have been fascinated in the use of encryption and the dual nature of encryption. When protecting information and communications, encryption actually has numerous benefits for everyone from governments, the military, to corporations and individuals. On the other hand, some of the same mechanisms can be used by threat actors as a method of evasion and obfuscation, right? So to avoid being detected. Now, historically, even governments have tried to regulate the use of and exportation of encryption technologies, right? A good example is the Wassenaar Arrangement, which is a multinational arrangement with the goal to regulate the export of technologies like encryption. Another example is the allegedly U.S. National Security Agency, or NSA, backdoor in the dual elliptic curve deterministic random bit generator, or the dual EC DRGB. And this, is actually done to allow for clear text extraction of many algorithms seeded by the pseudo-random number generator, right? By that dual EC DRBG. Now, some folks have shared the idea of encrypting everything. In that case, encrypting everything will actually have very serious consequences, not only for law enforcement agencies, but for incident response professionals, right? Something to remember about the concept of encrypting everything is that the deployment of an end-to-end encryption is difficult and can leave unencrypted data at risk to an attack. Now, there are many security products, including the next-generation IPS and next-generation firewalls, that can intercept, decrypt, inspect, and also re-encrypt or even ignore encrypted traffic payloads, right? Several people consider this a man-in-the-middle attack, right? And have many, privacy concerns. On the other hand, you can actually use metadata from network traffic and other security event sources to still be able to investigate and solve security issues. You can obtain a lot of good information leveraging things like NetFlow, firewall logs, web proxy logs, user authentication information, and even passive DNS data. Now, in some cases, the combination of these logs can make encrypted contents of malware payloads and other traffic fairly irrelevant, right? So, of course, this is as long as you can detect its traffic patterns to be able to actually remediate the incident. It is important to recognize that from a security monitoring perspective, it is technically possible to monitor some encrypted communications, like we mentioned before in the case of next-generation IPS and next-generation firewalls. However, from a policy perspective, it's a different story, right? Especially depending on your geographical location and also your local laws around privacy. Now, another technology that introduces some challenges to security monitoring is the network address translation, or NAT. By using NAT, a firewall or a router hides the internal private address from the unprotected network or the internet and exposes only its own address or a public range of addresses or a predetermined address, IP address. Now, this enables a network professional to actually use any IP address space as the internal network, right? Now, NAT, or network address translation, can present a challenge when performing security monitoring and analyzing logs, right? And also when analyzing NetFlow and all the data, since device IP addresses can be seen in the logs as the translated IP address versus the actual real IP address, right? In the case of port address translation, or PAT, this could even be more problematic since many different hosts can be translated to a single address, making the correlation almost impossible to achieve. Now, there's some good news. A few security products, such as the Cisco Landcope StealthWatch system, provides features such as NAT stitching that can be used with NetFlow and other data in the network to actually be able to correlate and map translated IP addresses in a NAT environment, right? Now, this accelerates the incident response task and also ease the continuous security monitoring operations, right? Another technology that introduces some challenges to security monitoring is DNS tunneling, right? Attackers actually have developed software that enabled tunneling over DNS for years, right? They actually have been using this to exfiltrate data from their victims for years. These threat actors like to use protocols that traditionally are not designed for data transfer, since they're less inspected in terms of security monitoring, right? So undetected DNS tunneling, otherwise known as DNS exfiltration, represents a significant risk to any organization. Now, in many cases, malware can use base64 encoding and other types of encoding to put sensitive data, things like credit cards, personal identifiable information, and other type of sensitive information in the payload of DNS packets to actually, exfiltrate that data from their victims. These are some examples of encoding methods that actually can be used by attackers, right? So including base64, binary encoding, NetBIOS encoding, and also hex encoding. There are several utilities that actually have been created to perform DNS tunneling, right, for the good and also for the bad. Here I'm actually including a few examples for your reference, right? So one thing to highlight is that some of these tools were not created with the intent to steal data, but cyber criminals actually have used it for years, for their own purposes, right, to exfiltrate data from the network. Another tool that presents some challenges to security monitoring is Tor, otherwise known as the onion router, right? Many people nowadays use tools like Tor for privacy. Tor is actually a free tool that enables its users to actually surf the web anonymously. However, Tor actually works, by routing IP traffic through a free worldwide network consisting of thousands of Tor relays, right? That's what we call Tor relays. Then Tor actually constantly changes the way it routes traffic in order to obscure a user's location from anyone monitoring the network. The usage of Tor also makes it more difficult for security monitoring and incident response, right? Since it can be hard to attribute and trace back the traffic to a specific user or of a specific user, right? So different types of malware are also known to use Tor to actually cover their tracks and actually to communicate between the malware and the attacker, right? So this onion routing is actually accomplished by encrypting the application layer of a communication protocol stack that are nested, just like the layers of an onion, thus the name the Onion router. The Tor client encrypts the data multiple times and sends it through a network or a circuit. And that includes randomly selected Tor relays, right? Each of the relays actually decrypt a layer of the onion and then reveal only the information to the next relay, so it can then route the remaining encrypted data and then so on, and reach the destination. Here I'm actually showing the Tor browser, right? There you can see the Tor circuit where the user actually accesses cisco.com from the Tor browser, right? So it first went to a host in the Netherlands, then a host in Sweden, a host in France, and finally to cisco.com. Tor exit nodes are basically the last Tor node or the gateways where the Tor encrypted traffic exits to the internet, right? So a Tor exit node can be targeted to monitor Tor traffic, right? Many organizations block Tor exit nodes in their environment to actually, protect, their communications and to actually make sure that no internal devices are actually using Tor. Now, the Tor project actually has a dynamic list of Tor exit nodes that makes, this task a little bit easier. This is actually the Tor exit node list that actually can be downloaded from the link that I'm actually sharing in here from the torproject.org website. Now, security products like the Cisco Next Generation Firepower, appliances and Firepower Threat Defense provide the ability to dynamically learn and block Tor exit nodes, right? That's actually a beauty of these next generation platforms. Peer-to-peer communication also presents some security challenges, right? So the peer-to-peer is actually referred to as the distributed architecture that divides tasks between participants computing peers, right? In a peer-to-peer network, the peers are equally privileged, right? This is why they are called a peer-to-peer network of nodes. Now, peer-to-peer participant computers or nodes reserve a chunk of their resources like, CPU, memory, disk, and network bandwidth so that the other peers or participants can actually access those resources, right? This is all done without the need of a centralized server. In peer-to-peer networks, each peer can be both a supplier as well as a consumer of resource or data, right? A good example was the music sharing application, that was actually very popular in the 90s called Napster. Now, peer-to-peer networks not only have been used to share music, videos, stolen books, and other data, but even legitimate multimedia applications. Like, an example is Spotify, right? It actually uses a peer-to-peer network along with the streaming servers to stream audio and video to their clients, right? There's even an application called PeerCoin, also known as PPCoin, which is a peer-to-peer cryptocurrency platform that actually utilizes both proof of stake and also proof of work systems to actually do, Bitcoin mining, and, cryptocurrency transactions, right? Now, universities like MIT and Penn State actually have created a project called Lionshare, and that is actually designed to share files among educational institutions globally, right? So again, not only for the bad, but also peer-to-peer actually has been used for the good as well, right? Now, from a security perspective, peer-to-peer systems introduce a unique challenge, right? Malware has actually used peer-to-peer networks to communicate and also to spread, other instances of the same malware to victims, right? So many free or stolen music and movie files usually come with a surprise of malware as well, right? So that's one thing to actually keep in mind. Additionally, like any other form of software, peer-to-peer applications are not immune to security vulnerabilities, right? This, of course, introduces risk for peer-to-peer software to be more susceptible to remote exploits due to the nature of the peer-to-peer network architecture. Another challenge is actually to keep network telemetry and logs from all sources in sync. Now, server logs, endpoint logs, NetFlow, syslog data, and any other security monitoring data will be useless if it is actually showing the run date and the run time. This is why it's a best practice that you should configure all network devices and your servers and everything to actually use network time protocol or NTP. So by using NTP, we ensure that the correct time is set, and it's also synchronized between all the devices within the network and all the sources of telemetry. Another best practice is to try to reduce the amount of duplicate logs, right? Now, these best practices will save you time and will also increase your operational efficiency whenever you're monitoring your network.